In this video, we're going to start looking at trigonometry and focus on identities. We've seen some examples of identities before. One could be x plus 2 all squared, and we could write this now as x squared plus 4x plus 4. This is an identity, and I've used the identity symbol. When we have an identity, it will hold true for all values. So if I looked at this one now and I substituted x is equal to 1 in the left hand side, we'd have 1 plus 2, which is going to give me 3. 3 squared is going to give me 9. If I substituted now into the right hand side x is 1, that would give me 1 plus 4 lots of 1 plus 4, and that would also give me 9. We can see that this holds true for all values of x. This differs to an equation. So for example, if I had the equation 2x minus 1 is equal to 5, we would look for the specific value of x that satisfies this equation, rather than now the identity holding true for all values of x. What we're going to do is look at two different trig identities. The first one is that if we have sine x divided by cos x, we get tan x. So writing this one down will help with your work throughout the unit. So if you want to jot that one down, that's the first one. Now, as long this holds true as long as cos x does not equal 0, and we'll look at that shortly, as division by 0 is undefined. The next one is that cos squared x plus sine squared x will give us 1. This is another very important identity. So cos squared x plus sine squared x, or if you like, the other way around, will give us 1. We can also manipulate this to write now sine squared x in terms of cos squared x. We could do it the other way around, or we could simply write sine x in terms of cos x, or cos x in terms of sine x. So these are your two identities that you need to commit to memory and apply throughout the unit. So let's just look at this idea of sine x, cos x and tan x. These are what we call now trig ratios. So if we took now a right angle triangle and we have an angle theta. Now that angle might be theta or it might be x. If we look in this case at the sine of theta, the sine of theta is going to be now the opposite over the hypotenuse. So that's b over c, or in general we can say now the opposite over the hypotenuse. If we look at cos or cosine of theta, what we're going to have is the adjacent over the hypotenuse, which is going to be a over c. Now in general we could write that that is the adjacent over the hypotenuse. If we look now at tan theta is going to be the opposite over the adjacent, which is going to give me now b over a. And in general, we can say that this is the opposite over the adjacent. And we've seen these before. So what we're going to do is just look at how those identities are derived. If you want to switch off for a couple of minutes, you're more than welcome to do so. If you're merely learning this by rote and just want to apply those, that's perfectly fine. What I'm just going to do though is show why these hold true. So a couple of ways of doing it. A nice straightforward way is to look now at the first one, and we'll look at sine squared theta plus cos squared theta. So as long as my angle is the same, I can't have sine squared 2 theta plus cos squared theta and write that as 1. So let's go ahead and look at this. What we can say on here, as we've just seen, sine theta is going to be equal to now b over c. If I take cos theta, that is going to give me now a over c. Just consider now Pythagoras. That's a squared plus b squared is equal to c squared. So if I look at that, what I can write now is that a squared plus b squared is equal to c squared using Pythagoras Theorem. What I'm going to do at this stage now is divide through by c squared. That's going to give me now a squared divided by c squared plus b squared divided by c squared is equal to 1. If we consider what we've got here now, we've got sine theta is b over c. So we've got b squared over c squared, which gives us sine squared. I suppose I should have written this the other way around, really doesn't matter. And then if we consider cos theta, we've got now a over c, and this would give us cos squared theta, a squared over c squared. Now we can see that this gives us 1. So that now is what we would call it a representation or demonstration rather than necessarily a proof. It's a demonstration that this will now give us sine squared theta plus cos squared theta will always be 1. If we look now at tan theta, so tan theta, we've already seen now that tan theta is sine theta over cos theta. So if we just consider now, we can see that tan theta is going to be b over a. So we can write now that tan theta, we've got on here now sine theta, which is going to give us a b over c, divided now by cos theta, which is going to be a over c. The c's are going to cancel, and that's going to give us now b over a, which we can see from here. So that's another demonstration that these hold true by taking now these values of a, b and c. So that's one way of showing it. An alternative way is to look now at a circle. I think the circle is beneficial, especially when you're working with angles. And what I'll do, I'll just spend some time on this. So if you feel that that's enough for you to move forward, you can go ahead and do that. What I'm going to do is just take this circle. Now this circle has a radius of r and an angle subtended with the x-axis of theta. So let's just go ahead and put this on. So if I just put a little right angle just here, what we're going to have now is the following. This length right here, if we've got the coordinates here of x, y, this is going to be x, and this length is going to be y. And that will always be the case around this circle with now the radius of r. If we just consider now the length right here, what we're going to look at is this length right here. So we can say now, using right angle trig, if we want the opposite, we can say that y is equal to r sine theta. So y is equal to r sine theta. So let's just write this down. If we look at this length right here, we can say now that x is equal to r cos theta. So that's using basic trig ratios to get the length of the opposite and the adjacent of this right angle triangle. If I go back to Pythagoras now, what we can say is x squared plus y squared is going to be equal to r squared. So if I take this right here, what we're going to have, x squared, well that's going to be r squared cos squared theta. Now you'll see that I'm writing the positive power here in front of the angle. That's standard notation. We don't put it next to the theta, as that would give us cos theta squared. We could bracket it off and put cos theta squared, but this is a general notation we use. Y squared is going to be r squared sine squared theta, and of course now using Pythagoras, that's going to give us r squared. Dividing through by r squared, we can see cos squared theta plus sine squared theta is going to be equal now to 1. So that's another demonstration. The advantage of this method is now when we come round to angles that are multiples of 90 degrees, especially when we're looking at tan theta. So if we look now, tan theta, let's just put this here, tan theta, based on my diagram, is going to be the opposite over adjacent, which is going to be y over x. So what we can say then is now that tan theta is going to be equal to y. Well, y is r sine theta, so r sine theta over r cos theta. The r's are going to cancel, and we can see now it's sine theta over cos theta. The issue comes is when we have odd multiples now of 90 degrees. Tan is undefined for odd multiples of 90 degrees. So what I should write just here now is that theta, and this is what we can write it, can't be equal to 2n minus 1 multiples of 90 degrees, or if you like, pi by 2 radians. So we can't have that. And the reason is, if we consider now, if I take this line up to the top, let's go ahead and do that. If I take this here, let's just put a different colour on. That's not going to show up. Let's choose this one. We'll go for that one. Hopefully that'll show. Still not too great. Let's go for another one. Let's see what this looks like. There we go. Okay, now if this was the opposite of the angle, what we've got is an adjacent of 0. So what we would have now is the value of x being equal to 0. So we would have now y over 0, and that is undefined. So when we say now that tan theta holds true for all values, it doesn't hold true for odd multiples of 90 degrees. Because if we look at it now, the adjacent of this particular triangle would be 0. Division by 0 is undefined. So that's looking a bit further into it. As stated, you can take that and use it if you want, but if not, all we need to be concerned with, if you just want this purely algorithmic and purely based on some two identities to learn, these are them. Sin x over cos x is tan x, or sin theta over cos theta is tan theta, as long as that angle is the same, and cos squared x plus sin squared x gives us 1. Okay, so let's go ahead and look at answering some questions based on those. So in question 1, it says, using the triangle below, show that sin x over cos x is equal to tan x. So if we just do this, what we've got then is that the sine of x is equal to the opposite over the hypotenuse. So that's going to give me 3 over 5. Cos x is going to be equal to the adjacent over the hypotenuse, which is 4 over 5. If we look at tan x is going to be the opposite over the adjacent, which is 3 over 4. So what we can write then is that sin x divided by cos x is going to give us now 3 over 5 divided by 4 over 5. The 5's will cancel, and that's going to give us 3 over 4, which, of course, is the value of tan x. In part B, we need to show that sin squared x plus cos squared x gives us 1. So what we've got then is sin squared x, which is going to be 3 over 5, which we need to square, plus 4 over 5, which we need to square. So this gives me now 9 over 25, plus 16 over 25, adding together 25 over 25, and that, of course, is going to give us 1. Therefore, we've shown it now with a specific example with values on. This can be either way round. Sin squared x plus cos squared x is equal to 1. We could write this as cos squared x plus sin squared x. Okay. In question 2, we're asked to simplify the following expressions. So what we've got here is sin 3 theta over cos 3 theta. Whenever I'm doing a proof of an identity or I'm doing any simplifying, I write to the examiner the identities I know. I know that cos squared x, or cos squared theta, plus sin squared x, or theta, in this x in this case gives me 1, and that tan x is going to give me now sin x over cos x. It takes me 10 seconds to write them out, but if I'm doing any show that questions or proof questions, I just want the examiner to know what I know instead of sort of going through it and just not showing clear workings. So sin 3 theta over cos 3 theta, well, that's just going to give me tan 3 theta. It doesn't matter that that's 3 theta, as long as this is 3 theta and that is an 8 theta, that's perfectly fine. Okay, this one here, we got 4 sin squared 2x plus 4 cos squared 2x. If I take the 4 out, that gives me 4 lots of sin squared of 2x plus cos squared of 2x. We know that sin squared x plus cos squared x gives us 1. It doesn't matter that this is 2x. We simply write that that is 4 lots of 1. As I've shown the examiner, I know what I'm doing here. Therefore, the answer is going to be 4. Okay, this one right here doesn't look like anything we've seen before. Now, if cos squared x plus sine squared x is equal to 1, we can manipulate this. We can write that sine squared x gives us now 1 minus cos squared x, just rearranging. We can say that cos squared x gives us 1 minus sine squared x. So all I'm doing is manipulating these identities. If you want, you could say that sine x is equal to plus or minus the square root of 1 minus cos squared x. And of course, cos x would give us now plus or minus the square root of 1 minus sine squared x. So all I've done is taken this identity and simply now manipulated it to rewrite either sine squared in terms of cos squared in terms of sine squared, or sine in terms of cos, and then cos in terms of sine. So let's factor out the 3 in this one. So that's going to give me 3, then we're going to have 1 minus cos squared of 5x. Okay, so let's look at this now. We've got 1 minus cos squared x gives us sine squared x. So I can write this now as 3 lots of sine squared 5x, and that now is simplified. I've just taken my identity that's been rewritten and gone ahead and just tidied that up. So that would be the simplified expression. Okay, let's look at this one. What we've got here is sine squared 4p, and we got sine 4p. I'm just going to rewrite this, and I'm going to write 3 times the fraction sine 4p multiplied by sine 4p, and that now is going to be over sine 4p multiplied now by the square root of 1 minus sine squared 4p. Actually, over time you won't need to do this. Once you see a power of 2 and a power of 1, you will simply now divide through. So what we can see from here is that we end up with this scenario. Okay, let's look at this. We've got 1 minus sine squared of 4p. We could write this now as cos of 4p. All I'm doing is simply using this one. 1 minus sine squared 4p, the square root of that is going to give me cos 4p. So we end up now with 3 lots of sine 4p over now cos 4p. We know that sine x over cos x gives us tan x, so we're going to have now 3 tan of 4p. And that now, as long as cos 4p doesn't equal 0, that, and I'll just put that there, now cos 4p, so cos 4p cannot be equal to 0. So that's the essentially the condition for this to hold true. So all I've done is simply manipulated. Knowing these is good, being able to rearrange them and simplify expressions is going to be a must. These take plenty of time to get cool with, but once you are, they are relatively straightforward, especially when we only have 2 identities. Okay, let's move on. Show the expression sin x plus cos x all squared minus sin x minus cos x all squared can be written as k sin x cos x stating the value of k. So let's expand this out. If I expand this out, we're going to get sin squared x plus sin x cos x plus cos x sin x, which we can write as 2 sin x cos x. Then on here, we're going to get plus cos squared x. From this, I'm now going to subtract. We're going to have sin squared x. Then we're going to have sin x cos x sin x. So that's going to give us now minus 2 sin x cos x. And then we're going to get plus now the cos squared x. So if I expand those brackets, this is what I'm going to get. I'm going to write to the examiner again that I know that sin squared x plus cos squared x will give me 1. So that is the identity if you want to write it here. So what we've got here now is sine squared x plus cos squared x. So this is going to give me now 1 plus 2 sine x cos x. And we're going to subtract from that now if we consider that we've got sine squared x plus cos squared x. That's going to give me 1 minus the 2 sine x cos x. So we end up now, if we do 1 minus 1, that's 0. 2 sine x cos x minus negative 2 sine x cos x is going to give us now 4 sine x cos x. And we can write now that k will be equal to 4. So that's done. So all I've done is shown the examiner I know what I'm doing. I've expanded these out, and we've ended up now using the identity to simplify, and we got 4 sine x cos x. Although not included in this particular unit, which you'll learn later, and I'll just scroll down to keep out the way, we can say that sine of 2x gives us now 2 sine x cos x. You don't learn this in the module here, but it is an identity that you will meet later on. So again, this could be written now as 2 sine 2x. Don't need to know it, that's all we needed to do, and we've shown clearly with the expansion here that that is what we're going to get. Okay, let's have a look at another question. We're asked to prove the following identities. Now, when we're proving identities, we can consider a range of different approaches. The idea is to start with the more complicated side in general. So what I need to show in the first one is that sine squared x minus cos squared x over sine x plus cos x is the same as sine x minus cos x. Okay, we can either make now the left-hand side look like the right-hand side, we can make the right-hand side look like the left-hand side, or we can change them both to look like something that's the same. With this particular one now, I'm going to start on the left-hand side, the more complicated side, and show that I can write it like the right-hand side. Don't worry if you don't get these to begin with, they take a lot of time and a lot of messing about. So before I start with identities, what I'm going to do is just write to the examiner that I know sine squared x plus cos squared x is going to give me 1, and that sine x over tan x gives, sine x over cos x, apologies, gives me now tan x. Whenever I start identities, I don't take for granted that the examiner knows this, so I'm going to show full workings. So these are my identities, and I will leave them there. So let's start on the left-hand side of this one. This is a difference of 2 squares. So if we had now a squared minus b squared, we could factor this now to a, let's put this as a plus b, and then we're going to have a minus b. So what I can write is that this is going to be sine x plus cos x, and then we're going to have this now multiplied by the following. This is going to be sine x minus cos x. So this is now the left-hand side. So if you just want to state to the examiner we're dealing with the left-hand side, you can do. We've got now sine x plus cos x in the denominator. These will cancel off, and that now just gives us the sine x minus cos x as required. So let's just see if I can squeeze that on. And you can write as required. An alternative is to write QED, which is Latin now for that you've shown the proof. I never write it just in case I made an error. You look a bit silly if you're going to put QED and then you've got your proof wrong. So all I've done is looked for the difference of squares. I'm always looking for things like the difference of squares. I'm looking for identities. I'm looking for different ways things can be written. So for example, on this one, I'm thinking to myself, well, tan 3x, that's sine 3x over cos 3x. So how am I going to manipulate that? Okay, so let's go for this one. So what I'm really aiming for now is to think, can I get an expression that looks like sine 3x over cos 3x? What I'm going to just do is write to the examiner, so we'll start just here. we can say now that and this would be at the top of my page, we could say now that the square root of 1 minus cos squared 3x is going to be now sine 3x. Remember, we've seen that before, so we've got now that the square root of 1 minus cos squared 3x is going to give us sine 3x. We've got now on here that the square root of 1 minus sine squared 3x is going to give us cos 3x. So I'm going to write to the examiner that we have now sine 3x, so sine 3x over cos 3x, and that now gives me tan 3x as required. So, and I could write here as required, but we would need these references here at the top to show that we've done that. Okay, let's look at the next one. Again, writing these out, just write them out. Sine squared x plus cos squared x will always now give us 1, and that sine x over cos x is going to give us tan x. It's going to take me 10 seconds to write those, but the examiner knows that I'm referring to them as I'm simplifying and showing my proofs. So these are my identities. Right, this one. We've got sine to the 4th power of x minus cos to the 4th power of x, and we need to show that looks like 1 minus 2 cos squared x. I think again the left hand side is more complicated. Now when I say complicated, complicated gives rise to more manipulation of identities. So for example, now if I wrote this one, I could think, well, that looks like sine 3x over cos 3x, and then I could go backwards and write these. But just seeing that this is more complicated or has more opportunity for manipulation, then I can use that instead. Okay, again, I'm spotting the difference of squares. So what I've got here now is sine squared x plus cos squared x multiplied now, so this is the left hand side, so if you want to state to the examiner you're working on the left hand side, and then we're going to have now sine squared x minus cos squared x. So what I'm going to have now, sine squared x plus cos squared x is 1. So I'm going to have 1 lot of sine squared x minus cos squared x. Whilst you don't need to be massively, what word am I looking for? Massively detailed in your working, I'm going to put this. I don't want to lose marks. This would be a 4-mark question, 3 or 4 mark question. I want to show the examiner, but I know this is 1. So what I've got then is sine squared x minus cos squared x. We can see the right hand side of that identity is devoid of a term in sine or sine squared. I know that we can write sine squared x as 1 minus cos squared x, and then we've got minus the cos squared x. So what I'm doing here now is using these identities and referring to them. Sine squared x is 1 minus cos squared x. So this gives me 1 minus cos squared x minus cos squared x, and 1 minus 2 cos squared x as required. So what I've done is focused on manipulating now the left hand side, spotted the difference of 2 squares, used my identities, I've got them up here, I've plugged them in, and we simply show that. So with this one, what we could have shown is we could have had 1, if this was in terms of sine squared x, we could have had now here, if it said, for example, 2 sine squared x minus 1, then we could rewrite this as cos squared x is equal to 1 minus sine squared x, substituted that in and rewritten it. So that's nice and logical. A nice identity to prove. As you can see, spotting, knowing those difference of squares, manipulating the identities and writing them out. Okay, let's look at this one right here. So cos x over sin x plus sin x over cos x is now 1 over sin x cos x. Again, I'm not going to start with the right hand side. I'm just going to add these fractions. So if I added the fractions, the common denominator now would be sin x cos x. That would now leave me cos x. So we'd have cos x multiplied by the cos x, and then we're going to have now sine x multiplied by the sine x. So that now is going to be the left-hand side. So I'm working again on the left-hand side. I've got my identities at the top of the page to show the examiner. So what we've got is cos squared x plus sine squared x. Cos x multiplied by cos x is cos squared x. Sine x multiplied by sine x is sine squared x. And that's over sine x cos x. We know that this gives us 1, therefore we're going to write this as 1 over sine x cos x, and that is going to give us, now let's make that a bit clearer, and that is going to be now the right hand side. We can say as required. So all I've done is use my identities again after now adding the fractions. I've started on the left hand side as I've got more room to manipulate now those identities. So there we go, nice and logical, and 4 relatively challenging identities to prove. Again, you'll need to be comfortable with them. Right, let's move on. Okay, in question 5 it says given sine A is 3/5 and that A is obtuse, find the values of A cos A and B tan A. Okay, we can do this purely with identities. I don't like to do it with identities. I like to consider this now as a bit of a sketch. So what we're going to have is the following. We're going to have some coordinate axes that look like this. If we think about this now, we've got an obtuse angle. This is 0. This now is 90, or we could write pi by 2 radians. This is going to be 180, or pi radians. This is 270, or 3 pi by 2 radians, and this is going to be 360, or 2 pi. These now are the acute angles in the first quadrant. We're going to have now, and I'll put them just there, let's just move them up. We've got now, and in fact we'll put them over here, let's keep them that way. These are the acute, so these are the acute. These are the obtuse angles. Remember, acute are less than 90, obtuse 90 to 180, and then down here we have now the reflex. So we've got the reflex angles down here. So what we've got here is that sine A is 3/5. And you might be thinking to yourself, well, this is a bit long-winded. Why am I bothering doing that? So we got, let's just put A here. So we could represent it like so. This is a representation and not necessarily the only way it can be drawn. Right angle triangle. So that is 3, that is 5, therefore this would be 4. Okay, so we got the sine of this angle A is 3/5. What we need to consider here are the values of each. If we go back to what was called the cast diagram, we know that all values in the first quadrant are positive. Only sine is positive in the second quadrant, only tan is positive in the third quadrant, and only cosine is positive in the fourth quadrant. So all are positive here, only sine is positive here, only tan is positive here, and only cosine is positive here. So if we look now, we can say that cos A is going to be equal to the adjacent over the hypotenuse, but because it's in this second quadrant and it's an obtuse angle, it will be negative. So negative 4/5. If it was in the first quadrant now, it would be positive. If we look now at tan A is going to be the opposite over the adjacent. That's going to be 3/4. Again, that is going to be negative. This is borne out, and I'll quickly sketch this, as I just think it adds a bit of completeness. What we'll have, in fact, we'll just draw 3 of these. When we're talking about now the values of sine and cosine, let's just get rid of that one. The values of sine, cosine, and tan, where they're positive, I'm just going to draw these now, and this goes back to our graphs of trig functions. If I draw y is equal to sine x, we start at 0, come round, back to 180, round like so. So this now is 0 to 90. So this is the point 90. We can see that it's positive here and we can see it's positive here. It's above the line. So this is y is equal to sine x. If we look here, and remember this point is 180 and this point is 360, we can see now that in these two quadrants it's negative and negative, and that's where this comes from. Positive, positive, negative, negative for sine. If we draw the cosine curve, we come down, round, down to the bottom, we come up, and like so. So this here is 90, this is going to be the point 180, this is 270, and then we're going to have 360 just here. Positive here, so just writing this here, y is equal to cos x. We've got now these two quadrants. This is the second quadrant, 90 to 180, negative. 180 to 270, negative. 270 to 360, positive. So when we say that cosine is positive in the fourth quadrant, and it's only cosine positive, that's what we have. If we draw tan, what we have is something that looks like this. It's got an asymptote just here at 90 degrees, and then we come round like so, and up, and then we'll have something like this that comes round, and then another asymptote. These asymptotes now are every 180 degrees, and then we'll have something like this. So this now is y is equal to the tan of x. So this is positive, first quadrant, up to 90. This point now is going to be 270. That is 180. So what we can see, it's negative here, but it's positive now in the region from 180 to 270. And then it's negative from 270 to 360. And that's why we've got this third quadrant, positive, positive for tan. So that gives you some idea. That's where it's born out of. So that helps me in terms of the sketch to determine the signs. What you could have done, and this is a bit haphazard, you could have said now that cos A, so cos, in fact I'll write it as cos squared A is plus sine squared A, so plus sine squared A gives us now 1. So what we could write now is that cos A is going to be now equal to plus or minus the square root of 1 minus sine squared A. So if we look at this, if we wanted cos A, what we could have done is the square root of 1 minus now sine squared A, which is going to give me now 9 over 25. We can see that this gives us plus or minus 1 minus 9/25 is 16/25. And we can see that this now gives us plus or minus now 4 over 5. The problem is we've got a plus or minus, and that's why we need to consider that if it's an obtuse angle, we need now the negative value, and that's why I prefer sketching it. The reason I like to sketch it is because it's clearer to see. If you merely use an identity, you end up with this solution of plus or minus 4/5, and often students don't even put the plus or minus there. The same if we look now at tan A, well what we've got is that tan A is going to be now sine A over cos A. And of course what we would look at now, if we didn't know the signs, we would simply say that this is going to be 3 over 5 over 4 over 5. But remember this is negative, so it would give us negative 3 over 4, which we can see by the diagram. So that's why I like a diagram and like in these particular things. This is just to show why the different quadrants are there, so the little sketches. It's entirely up to you if you use them. We spent a long time on this question, but again, once you understand this particular approach, I think it's significantly easier than blindly plugging into the formulae or the equations as such and not understanding where each function is positive or negative. Okay, let's look at another question. Right, what have we got here? Okay, given that x is equal to 3 cos A and y is equal to 2 sine A, we need to write an equation connecting x, y and x. Okay, so what I'm going to do is just again write to the examiner that cos squared A plus sine squared A will give us 1. So what I'm going to do is look now for an expression for cos A. So I'm going to write now that cos A is going to give me now x divided by 3. If we look at sine A, well, sine A is going to be y divided by 2. So I need an equation connecting y and x. So I can write now on here, either way round, remember this is perfectly fine. Sine squared A plus cos squared A will give us 1. So what I can say then is now that y over 2 squared plus now x over 3 squared will be equal to 1. So if we want, we could leave it like that. All it's asking me for is an equation connecting y and x. It's not asking me to express y in terms of x. It's just now asking me to write an equation connecting them. That's it. If you want, you could write that this is y squared over 4 plus x squared over 9, and that is going to be equal to 1. If you really wanted, you could write 9y squared plus 4x squared is going to be equal to 36. I think that's the most simple form. And again, you could rearrange and express y in terms of x. I'm not going to. This would be my answer just here. All they've asked for is an equation connecting y and x. So I've used a trig identity to do that. And in later studies, when you look at different types of curves, this will come in to your work. But for now, that's all we would need to do. So there we go, trig identities. We've been going about 40 minutes. Hopefully that's been a good introduction. It has been quite theory heavy certainly in some points, especially here and the initial introduction, but I do want to be robust in the understanding of this rather than just plug in and chug in, as I would say. So an introduction to trig identities.